Hello everyone, my name is Sakshi Bhavsar and today I will be presenting my report on the 2024 paper titled Federated Adaptive Federated Learning with Differential Privacy. This research falls under category 4, which is secure data sharing, in category 7 of our course, specifically privacy preserving techniques. In a world where data is decentralized, this paper provides a roadmap for training high-quality machine learning models without ever compromising individual user privacy. Today, I will walk you through how the authors achieved a major breakthrough in both speed and security. So the second slide states that the privacy utility trade-off. The primary motivation for choosing this paper is the inherent conflict we often discuss, the trade-off between privacy and utility. While differential privacy is the gold standard for security, adding noise to a model usually makes it slow and less accurate. For industries like healthcare or finance, a model that is 500% accurate is useless, but a model that leaks data is illegal. I was fascinated by Federated because it claims to bridge this gap, offering a high-performance solution that doesn't sacrifice one for the other. So, moving to the third slide, it states about the system architecture, the three main pillars. The paper utilizes a three-tier architecture to ensure security. First one is federated learning, which allows data to remain on the client's device. Second is the differential privacy. Differential privacy is applied at the local level. The belt and suspenders approach means that even if the server is curious or the shuffler is compromised, the mathematical noise added to the gradients make it impossible to reconstruct the original raw data. And the third is shuffle model. So for thinking for the shuffle model, this is a secure intermediary that shuffles the updates so the central server can't link an update to a specific IP address or user. So for the first slide, what is technical innovation, or what is Federated? The core technical contribution is the Federated algorithm. In standard gradient descent, privacy noise causes the training path to become jittery or unstable. Federated introduces an adaptive learning rate. It looks at the history of the gradients to understand which directions are meaningful and which are just noise. In addition to it, they use gradient centralization. By using the gradient centralization, they have zero mean and unit variance. They stabilize the training process. This allows the model to learn efficiently, even when the privacy budget, which is represented by epsilon, is very low. So, moving to the fifth slide. Experimental setup. So to prove this theory, the authors used a TensorFlow based framework. So this framework is like it tests the algorithm on the MNIST, which is a benchmark of dataset. They set a very strict privacy budget of epsilon equal to 0.5. For context, in many real-world applications, an epsilon of 1.0 or higher is used. By choosing a lower number, the authors were essentially playing on hard mode to prove that their adaptive algorithm could handle high levels of noise better than traditional methods like standard DPSGD. And it is compared against DPFL and top-K sparsification. So the key results for it were observed, like the results were impressive. Federated achieved a final accuracy of 82.29%. However, the most striking part is the speed. It reached the accuracy in 12 iterations. Compare that to traditional privacy-preserving models that often require 50 or even 100 rounds of communication between the server and the client. This proves that FAD grid isn't just secure, it's computationally efficient, which is vital for mobile devices with limited battery life. So in the relevance of this course material, this paper is a direct application of our course modules on privacy enhancing technologies. It brings to life the theoretical concepts of differential privacy and anonymity through the shuffle mode. It also touches on access control, as the architecture ensures the central server only has access to aggregated, noised data rather than raw records. It is a perfect case study of how the principles we learn in the classroom are being implemented in modern high-performance computing. So for the extensions, for the AI extension, AI says that integrate secure multi-party computation, SMPC, so the aggregator only sees the final sum. So for my self extension, I would say that to test FAD grid on non-IID data. In the real world, data isn't distributed evenly. A hospital in New York has different data than a clinic in rural Texas. I would want to see if FAD grid's adaptive nature can handle these unbalanced data sets as effectively as it handled the uniform MNIST data. So, for the critical analysis part, my analysis of the paper is overall positive, especially regarding its efficiency. However, a significant gap is its assumption of a semi-honest environment. It doesn't account for poisoning attacks, where a malicious user intentionally sends bad data to ruin the model. If I were writing this paper, I would include a robustness filter or an anomaly detection step to ensure that the updates being shuffled are legitimate and not malicious. So for the conclusion and references, FAD Grad demonstrates that we don't have to choose between privacy and performance. By combining adaptive optimization with differential privacy in the shuffle model, we can build AI that is both fast and secure. Thank you for your time and for listening my presentation. I have listed my references on the final slide. Thank you.